Okay. All right, so let me say it again. End behavior of a function's graph is the behavior of the graph as x approaches positive infinity or negative infinity. So I don't know that you have space here, but you can just watch this part. Is suppose I have a graph, and let's take a really common graph we know, a parabola. End behavior, what they mean by as x approaches positive infinity. I'm going to write some new notation. As x approaches infinity, we're going to use an arrow, and we're going to use the infinity symbol. And what it means, and this is sort of what helps me, because students get all mixed up as to, is it what's positive, negative, infinity, and getting it all mixed up, is I like to imagine that I've tied a loose string to my parabola. And as I walk to the right, I'm pulling my string, okay? I need to maybe create some kind of a model of a parabola, and we do this with string, is that as I pull the string to the right, where does the graph go? Where does the y value go? Like I'm pulling this, I'm on this one, okay? I'm pulling my string and I'm walking. As I pull the string to the right, where does the graph go? As I'm pulling, isn't it going up and up and up, right? So what's happening is the y value, as I went to the right, is going up to positive infinity. Well, as x approaches negative infinity means as I pull my string and walk left, okay, it's like, okay, I've got my string and I'm walking and I'm pulling. Where is the y going as I'm pulling? It's going up. So the y value is going to positive infinity. We don't.
When you have a break in your class or at the very end of class, could you office for a minute?
Who?
Ian Huff.
This is third period Algebra 2, so I do not have Ian Huff.
Sorry.
That's okay. Okay, so now let's look at another common graph. This one's the x cubed graph. And we're going to talk end behavior. As x approaches positive infinity, so let's suppose we've tied a string to this graph, and as I start walking to the right, where does the y value go? It's going up. So y approaches positive infinity. But as I go to x is negative infinity, okay, x negative infinity is just moving left on the graph. So if I'm pulling my string, where does the y value go? It didn't go up, did it? It's shooting down. So y is going to negative infinity. If you're having trouble drawing the infinity symbol, a suggestion, a really basic one, is make two circles next to each other. I've heard students say they turn their paper sideways, make an 8, and then turn their paper back around. Whatever you need to. But my calculus students yesterday said to me, you know what, because we deal a lot with infinity in calculus, and they said, we can really do those symbols. We remember back in Algebra 2 trying to do them and couldn't do them, and now we can do them with ease. So it's really, really quite neat. All right, now we're going to do an exploration. I want you guys to go to your Y screen, take out your calculator, and we're going to just explore. In y sub 1, I want you to put x. Y sub 2, I want you to put x cubed. And in y sub 3, I want you to put x to the 5th. Well, I was messing around with my screen in my previous class, so to reset it back to a standard window, I'm going to press Zoom 6. And if you remember, we've done math aerobics previously. Remember how we did the V's and we did them up and we did them down and we stretched them and shrunk them and stuff like that. Well, we get to do some really cool math aerobics with this stuff. But what I want you to notice, and I'm going to do it backwards here or turn around, is that the line, if you think about this line, as x is going to positive infinity, as I would be pulling my string, it's still going to go up to positive infinity, right? And my x cubed just goes to infinity faster. That's the only difference. They're both really, either it's this or it's going up like this. So, and then as I move left, it's going to negative infinity. And we're just comparing, the rates are different as to how fast it's getting there. So what I need you to remember here is that if I have x to the odd power, as I go to positive infinity on x, the y goes to positive infinity. As I go left, on the x-axis, it goes to negative infinity, and the y goes to negative infinity. Okay? So go back to your y screen, and I want you to clear all three graphs out. And I want you to now type in negative x cubed in your y sub 1. Now we put it back on a standard window, so let's just put graph. And what happened is our standard was x odd, looked like this. Now when you put a negative in front, it's going to flip it. Okay, this is going to be really important. X odd with a positive out front, negative x odd. Alright, go back to your y screen and clear that out, and I want you to put in x squared, x to the 4th, and x to the 6th. Okay, so now we're going to look at power even powers, and then press graph. And so remember, there's our parabola. We knew that was touchdown. Remember we talked about that? That's touchdown. Well, an x to the 4th just gets there faster, and the x to the 6th does it even faster, but they're both touchdown. Okay? Now go back to your y screen, and let's clear those three out. And in y sub 1, let's do negative x to the 4th power. And press graph. So instead of the touchdown up, putting a negative out front turns it down, okay? So now we're actually ready to do the box for end behavior. If a is positive and you have f of x equals ax to some odd power, in general, the end behavior, now we might get some wiggles in the middle eventually. We're going to see those in a little bit. But in general, this is what it looks like. And so the end behavior is as x approaches positive infinity, instead of using the y, we're going to say f of x approaches positive infinity. On the left side, as x approaches negative infinity, f of x approaches negative infinity. So now we're generalizing what we were messing around with, okay? Now if a is negative, and I have ax to the odd, that reflects it, and so that we get a graph like this. And I've had a student once say, oh, like a snake, and it helped them to remember. So if that's a visual that would help you, x cubed or x to the 5th, the odds maybe look like a snake. Well, okay, if that works for you, terrific. So as x goes to positive infinity on the right side, f of x now goes to negative infinity. On the left side, as x is going to negative infinity, because I'm moving left along the x-axis, the f of x is shooting up, so it's going to positive infinity. All right, now we are going to look at this as columns, that a is positive down this column. So if I have f of x equals ax to an even power, in general, it's going to look like a parabola. And then the end behavior is as x approaches positive infinity, the y value goes to positive infinity, or we're going to write f of x. As x approaches negative infinity, the y value, or f of x, is shooting up. But that a is now positive. Now, if the a is negative, this reflects it over the x-axis, so it's opening down. And so the end behavior is as x approaches infinity, the f of x is shooting down to negative infinity. And as x approaches negative infinity, f of x is going to negative infinity. I do not want you to memorize this. I want you to analyze it. Okay? So what we're going to do for a moment is we're going to do some math aerobics. So people listening won't be able to see this, but here's what I want you guys to do. As soon as you're finished writing that down, I want you to put your pencils down, and I want you guys to stand up. And I want you to stretch out your arms so that you won't hit anybody beside you. So move in such a way that you won't hit anybody. And I'm going to do my best to do this backwards, okay? So hopefully I won't mess this up. But I'm going to call out a term, and I want us to do the end behavior with the arms. Let me give you a couple examples. If I said to you, x to the 4th, we're going to do a touchdown. But if I say to you, negative 3x to the 8, even, but it's a negative out front, so they're both down, okay? And if I said to you, x to the odd, snake. Wait. Am I doing, oh, sorry. I'm sorry, because I've got to do it backwards. Sorry. No, so this would be x to the 7th. Then, if I said to you, I have negative 4x to the 11. This one. All right, Hannah, come on. All right, you guys ready? So I'm going to call them out.
We don't have fun music this time?
No, not this time. No, this is on the fly. All right, so here we go. What if I tell you I have 9x to the 12? Touchdown. 9x to the 12. All right. Negative 8x to the 6th. There you go. They're both down. All right. 15x cubed. Good job. All right. How about negative 2x to the 5th? All right. Let's try to go a little bit faster now. Okay. All right. So here we go. Let's go x to the 16. X to the negative, oh, sorry. X to the 11. Negative 5x cubed. Negative 4x to the 8. 2x to the 10. 3x to the 7. All right, good job. Have a seat. This is fun. Okay, now, in your textbook, there's something called the leading coefficient test. And the leading coefficient test says this, that if you look at my next example, it says we want to graph f of x equals negative x cubed plus x squared plus 3x minus 3. Well, the end behavior, and what we mean by end behavior is not the wiggles in the middle, because these are going to get some wiggles. But in general, I look at the leading term, the negative x cubed. Okay, here's x cubed, here's negative x cubed. Which is unfortunate you can't see me doing my arms if you would watch this online. So, like, I know this is the general end behavior. Alright, so when you're graphing these, we're going to do x and y intercepts, minimum and maximum points, and we are going to use the calculator. For the y-intercept, though, we don't need the calculator. The y-intercept is you let x be 0, and what's really neat is you can see a connection to Algebra 1. Do you remember when you did y equals mx plus b? And you said, okay, to find a y-intercept, you let x be 0. That is true for all functions. And we're going to get to see in Algebra 2 a lot of different kinds of functions this year. So you're still going to let x be 0. So it's not new what a y-intercept is. But if I plug in that x is 0, what's the y value?
-3.
Good job, it's -3. Now to find an x-intercept, we let y be 0, and this one doesn't necessarily factor for us. So I want us to go to our y screen and clear out what we had in there. And we're going to enter the function in y sub 1. So I have -x cubed plus x squared plus 3x minus 3. Press graph. We should still be on the standard window. Now, I do want to warn you that when you graph these and you understand what the end behavior is, if you're not seeing part of the graph that you know, like you know this is supposed to come back down, and suppose my window shows me this, and you're like, wait a minute, I know an x cubed is supposed to come back down. That means as the user of the calculator, you have to adjust your window. So you do need to be prepared to do that. Okay, so the first thing is, let's find the x-intercepts, and let's review how to do this on the calculator. I want us to all do this together. Let's get this one that's on the furthest left. So we're going to go second trace. Number 2 is 0. Again, second trace, and then the word 0. I think it was number 2. Now, I want everybody to look at the board for me. Here's the x-intercept, or the 0. When it says left bound, I need that flashing cursor to flash to the left. It is. You press enter. Then it says get to the right. Just to the right of the x-intercept. You see mine's flashing to the right. You press enter. On the guess, you just press enter. So I have an x-intercept of -1.73, 0. Now, it looks like there's one, or there might even be 2 x-intercepts over there, but it's not clear on my graph. So, do not assume there's only one. You need to dig in and explore. So let me show you a really neat feature of your calculator that I'm not sure we've used before. Maybe we have. You press zoom, and number 2 is zoom in. Now what happens is when you press zoom in, there's a flashing cursor, and you need to move it to the region you want to zoom into. So I have not pressed enter yet. So I'm going to move really close to this, and then you press enter. Oh, there's 2. I would have gotten it wrong if I assumed that there was just 1. So now let's go through the process and find each one. Let's get the one on the left here. So you press second trace, number 2, and it says get the left bound, get the right bound. Now I'm just getting to the right of that one x-intercept. Oh, that's 1, 0. Okay, now go get the third one. You should be able to do this now on your own. Okay, now it says, did you guys get 1.73?
Yes.
Okay. Now I have a problem because I can't see the whole graph. So all you do is zoom 6. Put it back on the standard window, okay? Not a problem. Now we need to find what's referred to as the local minimum and the local maximum. That just means where there's a valley and a hill, okay? A valley and a hill. So we're going to go second trace, and let's go get the minimum. Well, when I look at this graph, here's the minimum. Can everybody have eyes on the board for a quick moment? Here's the minimum. So a left bound is I need it to be just a little bit to the left. And then you get a teeny tiny bit to the right of that and press enter on the guess. So I'm getting a minimum at -0.72, -4.3. And then let's repeat it and find the maximum. So I do second trace, max. Okay, I got my left bound. Now I'm getting a right bound. On the guess, press enter. Identify minimum and maximum in the body of your work. Now, do you notice I have 6 points? That's a lot of points. If you have 5 or 6 points, you don't need an additional table. That should be enough to make our sketch. But if you go through intercepts and min-max and you have 2 points, you need a table with a few more points, okay? So let's go ahead and draw this. Excuse me. Okay, so let's start plotting. Here's my y-intercept. I have an x-intercept, x-intercept, x-intercept. You are going to need to estimate where decimals are. So for my minimum, if I want negative 0.72, that's a little bit more than halfway, and negative 4.3. 1.39 is not quite as far as my x-intercept here at 1.7, and then 0.42. You are going to want to look at your calculator to see what's happening here. And then do you see the connection with the end behavior? I might have wiggles in the middle, but I still have the general end behavior that I'm supposed to. Okay, if you're comfortable with this, I want you to try letter B on your own. I'm going to give you a few minutes. Put g of x in the y screen. Find the y-intercept, the x-intercepts, and any minimum or maximum values. While you're doing that, I'm going to pass out tonight's homework. Tonight's homework, I'm going to modify it just a little bit. You are only going to do the worksheet I'm passing out tonight. You are not going to do additional bookwork. Okay, so it's a worksheet only. It's 15 problems. You will do all 15. Now, I'm also going to give you a complete solution sheet. But I want these back. I'm trying to be a good steward of my resources. I use a lot of paper in here, so I can reuse these year to year. It does not matter to me if you round 1 decimal place or 2. Whatever you're comfortable with is fine. Do you guys notice that there's 2 local minimums on this one? Do you see 2 places where there's a little valley? And something I want you to think about is that this is an x to the fourth with a positive in front. So the end behavior is a touchdown, and I really do have the touchdown, I just have some wiggles in there, okay?